All right, well, we're moving right along. We're now into session 11. We've learned to reference our drive. We've learned to do positioning. Now we're going to tackle a variety of miscellaneous advanced features. These are various capabilities within IPOS to do different kinds of things. You'll find that many of these features do apply when we pull everything together in your senior project, which is coming up in the not too distant future. So let's go ahead and learn a few advanced things about IPOS. The first thing we're going to talk about is using the multitasking capability in IPOS. Remember, you learned this long ago back in one of the early sessions. You can actually run 3 separate tasks simultaneously. These run independently of each other, and they can all handle different aspects of your program. Now, we haven't done any multitasking up to this point. We've only been relying on task number 1, which is the only task that has to run. Of course, when you click the lightning bolt, it starts task number 1. But now we're going to learn how to activate tasks numbers 2 and 3. So I thought it would be a good idea just to review some of the key ideas of multitasking. Of course, I've covered a few of my points already. We talked about what task number 1 is and how it's started in Movie Tools. Tasks numbers 2 and 3 are started in the program, and we're going to learn a function call that you use to activate or deactivate tasks 2 or 3 or both. Just a quick review how those tasks work. Tasks numbers 1 and 2 are deterministic. In other words, they have a very predictable execution time. Their execution time can actually be adjusted by tweaking 2 parameters, P938 for task 1 and P939 for task 2. Do remember the little rule that the time the tasks 1 and 2 occupy must be less than or equal to 12 instructions per millisecond. Don't adjust them so they're trying to execute more than those number of instructions per millisecond. If you do, some weird things can happen. Task number 3, remember, is not deterministic. It just uses whatever's left over, and it typically executes 20 to 40 instructions per millisecond. Can be faster, but it's not guaranteed. In fact, all they really guarantee you is 1 instruction per millisecond. As you can guess, tweaking your task's performance is something of a skill that you develop, and it can be tricky to get things right. And of course, let me just remind you, we're operating in the compiler language, not the assembly language, so we really can't relate lines of code in IPOS to instructions per millisecond, because one line of code in IPOS can turn into maybe dozens of assembly language instructions. It just depends what it is. So this information is provided for you, but do be aware that you need to take some of it with a grain of salt. Task management does require some skill. We're not going to get into anything really complicated with multitasking, but I'm going to show you a typical example of how you can use it to make your life a little easier. I'll also just mention parenthetically, tasks can be interrupted by an interrupt. We are not getting into interrupts in this class, although we may cover that in an advanced mini class down the road, but do be aware of that. All right, so that was the quick review. Now let's actually look at how we start up one of the other tasks. There is a task control function which takes care of this. It is called setTask, and it takes 2 parameters. It starts or stops one of the 2 tasks. Here are the parameters. There is st2 start and stop, and there is st3 start and stop. I think you can kind of guess what these parameters do. If you pass a start, it will start either task number 2 or number 3, and if you pass it a stop, it will stop that task. Pretty simple. Now, the question is, what is function? Function is the name of a user function that is going to run when the task is started. Remember, the main function is associated with task number 1, and it runs over and over and over. Well, there are equivalent functions for tasks numbers 2 and 3, except you get to create it and give it any name you like. And like main, it runs over and over and over at whatever speed the task is set to execute. So you just give it a task name. Let me give you an example of what the function call would look like. Let's say you want to start up task number 3. You would call setTask, you would say st3_start, and then you would pass it the name of the function. In this case, I've called it task3. Notice you don't have to include the empty parentheses there. All you need to do is make sure there is a function defined in your code called task number 3, and that will start executing, and it will just execute over and over and over. Okay, not too complicated. Now let me suggest an example of why you might want to start up another task. What might you do? Well, of course, there are all kinds of things to do, but here's something that is immediately obvious. Let's say we want to create a task that runs in the background and simply monitors everything that we care about. Things like the status word, the IOs. And we want it just to keep an eye on those things and maybe process them and put useful information into some variables that we can just look at in our main program as we're going along. Let me show you an illustration of this. This is something that I put in my programs very frequently because there are many things I want to keep an eye on. So what I do is I create a series of variables, and I've just declared them as longs, which means IPOS picks where they go in data memory. And I created one called inhibited to tell me if the controller inhibit input is on or off. I have one called enabled, which keeps an eye on the enabled input bit. I have one called ready, which gives me the VFD's ready status. I have one called referenced, which lets me know if the VFD has been referenced or not. Then the in position bit, which tells me if I've arrived where I'm traveling. I have a stopped bit, which monitors the motor's standstill status bit, tells me if the motor is moving or not. I have a fault bit, which indicates if the VFD is faulted. That's very helpful to know sometimes. And then I have my option inputs and outputs, where I keep an eye on the DO10 through DO17 and DI10 through DI17. So what I want these variables to do is just always have that information constantly being updated in them. So I'm going to do this in the background with task number 3, which is the everything else task. So I create a task handling function called task3. You can see it right there. And here's all it does. It goes through and it harvests all that information by looking at status word, by looking at inputs and looking at outputs and various other useful system variables. And it just keeps updating these variables. Very handy thing to do. And so I would just put this in my code. I'd create the variables. I'd create the task function. I would put it near the end of the program. And then I would start up task number 3 using that function call to launch it. From then on, I would just be able to ignore it and be confident that those variables would have the information I need being updated on a regular basis. All right, that's a very good application, and I recommend that maybe you take a good look at this because you can do something very much like this in one of the programs we're going to be writing shortly. Okay, just a few other things about multitasking. First of all, tasks 1, 2, and 3. A little warning, they are not synchronized with each other. They run totally independently of each other. You could say they are asynchronous with respect to each other. What that means is you may have to wait for something in one task to catch up with another. And one way you can do that if you want to be sure things have caught up is you could do a short wait function where you just wait a few milliseconds and give it time to happen. Another thing that you might have to do, of course, is tweak the performance of tasks 1 and 2 since they are deterministic and you can adjust their performance with parameters 938 and 939. Again, that's a borderline expert task that you'll probably get better at as you gain experience. All right, time to write a program. We are going to create a new program. We're going to call it program 12, but I would like you to copy the last program you wrote, which was that positioning conveyor program. Make a copy of it. You're going to modify it and tweak it, but it will become program 12. Here are the things you need to do. It has no change in its basic behavior, so it's still a positioning conveyor, but I'd like you to do a few things to make it a better piece of code. First of all, migrate the referencing and positioning code into 2 dedicated user functions, so take them out of main. I would like only the program's core logic, like the initialization and decision-making structures, to be in main, and then that logic in turn will call your user functions to reference and position. I would also like you to create a task3 function to do something just like I showed you a couple slides ago, to monitor the I/O and the status. Put code like that in there and activate that task in the initialization. And just to confirm everything's working, use your variable watch feature to check that those variables are updating regularly. Then, of course, run your program and make sure it still does its job, positioning and referencing. All right, pause the video and go do it. Okay, well, I hope that went well for you and you discovered the magic of multitasking. So let's take a look at my code and you can compare it to yours. All right, well, here is our modified program. This, of course, is our real unit positioning program for the canning and palletizing application, but we've modified it to use the background task using the multitasking feature. We've also made some improvements to the code, so what I'm going to do is kind of go through it section by section, show you what's changed, what stayed the same. We'll begin with the constants. First of all these constants are exactly the same as they were in the previous program. We have our station positions, our different times, our mechanical parameters, and then some constants that are associated with different output bits in opt-out IPOS. So nothing too different there. I've added two new constants called ref mode and pos mode, and I've defined these as 1 and 2. This is just to make my code more readable. I'll point out where I use these when we come to them. Also, there's one constant that's now gone. You may remember I had one called referenced that extracted the IPOS referenced bit from status word. We're not using that because the multitasking background task is going to check that bit and update a variable by that name instead. So I've removed that constant as unnecessary. All right, let's come to the variables that the background task is going to use. And here they are. What's going to happen is that background task, which is running as the multitasking task number 3, is going to continuously update these variables. It's going to harvest different status pieces of information from various locations. It's going to be checking the inputs. It's going to be checking the outputs. It's going to be checking status word. And each one of these variables is going to contain information about a particular thing. For example, the variable inhibited is going to show the controller's status input. It's going to be true if the controller is inhibited and false if it's not. Same thing with enabled and ready and referenced and in position, as well as stopped and fault. All of these are going to give simply a binary value, true or false, indicating whether that particular bit is set or clear. Then I have two variables, option inputs and option outputs, that will contain all the option card input bit statuses and output statuses. So we'll be able to assess the option I/O, both in and out. All right, so that's going to be updated by the background task. We'll take a look at that in just a second, but let's finish variables here. These variables down at the bottom have not changed. They are associated with the math that handles the positioning, translating real units to increments, so nothing different there. All right, so that's the variables and constants. Let's look at main. This has not changed enormously. All of this code is exactly the same. It turns all the option outputs off. It pauses for 5 seconds while the system stabilizes, and then it turns on the ready signal. It also computes the mechanical parameters using that pseudo fraction math to get the position scale factor. This, of course, is used for positioning. Nothing new here either. Now, something new at last. This is where we activate our background task. We call the function setTask, and we are going to activate task number 3, which, remember, is the everything else one. That's not deterministic. It just sort of runs using whatever time is available. We start it by passing in the constant st3 start and the name of the task handling function, which I've called task3. Kind of unimaginative, but it's descriptive at least. And that will start that background task running and updating all those status variables. Let's go look at that task right now before we cover anything else. It's at the very end of my program here in the user function section. And here it is, task3 function. Notice it's just called task3, empty parentheses because of course no parameters are allowed. And all it does is it just runs continuously over and over and over, and it just goes through, harvests the different bits and values from different places and puts them in those variables. So it brings in inhibited, which it finds in input level B. It's actually the very first bit. Notice the exclamation point there. We have to invert it because the drive is inhibited when that switch is turned off rather than on. So we have to flip the bit. When inhibited is true, it's a 1, and when it's not inhibited, it's a 0. So sometimes we have to flip a bit if its normal status is opposite what the name implies. Enabled, ready, referenced, in position, and stopped. We just harvest all those from different places, either from input level B or status word. Fault has to be inverted as well because the fault bit is opposite what you normally would think. Then we bring in the option input values from input level B. Notice we mask off just the bits we care about, the 8 bits of interest, and we shift them down to the bottom. Option outputs, that just lets us check the status of our outputs. So we take out P level B, we mask those, and that funny hexadecimal number is the way it is because the bits we care about are not down at the bottom of the word, they're kind of in the middle of the word. Remember, out P level B has both the standard outputs and the option outputs. So we have to mask off just the ones we want, and then we shift them down by 6 bits so that what's in the bottom of that variable is going to be the 8 option output bits only. All right, so that's our multitasking function, which is going to be running and just providing us continuous status information. Pretty simple. Let's go back now and look at our main code. We have our endless while loop, and the first thing we do is we clear the access stop. That's just in case it's been stopped in the past. We need to re-enable it so it can run again. Then we have a while loop here. I'd like to point this out. This is new. I added this in. I don't want to jump into either referencing or positioning if either my drive is inhibited or it's not enabled. So I put a while loop here and I say while it's inhibited or it's not enabled. If either of those is true or both, just sit and spin in the while loop. So this is one of those while loops with no code after it. It's just got a semicolon. So it's just going to wait until the drive isn't inhibited and it's enabled. And once that happens, the while loop will exit. And then we have an if statement. Actually, we have 2 if statements to determine what we're requesting. So we take option inputs, we mask it with the binary value 1, 1. We're looking at the 2 bottom bits. And if we're in reference mode, which means that DI10 is on, that'll give us a 1. Notice I use a constant there. I created that new constant back up in the constant section, and this just makes my code more readable. It's basically saying if the bit pattern for referencing mode happens, then call a function, do reference. And if it's not that, come here, do another if, look at those same 2 bits, and if I get a 2 out of that, which is binary 1, 0, then it's pos mode. And if that's the case, then call the function do position. Now, if it's anything else, it's going to do nothing. It's just going to loop back to the beginning of the while loop, start all over. One of the advantages of the way the code is written is if you have both DI10 and DI11 on at the same time, then it's not going to do either of these because that would actually give the value of 3 rather than 1 or 2, and that doesn't have any code to send it anywhere. So if you turn them both on, nothing will happen, and that's the way it should be. You shouldn't be able to have conflicting operations. Okay, so that dispatches either referencing or positioning to user functions. Now notice I've created user functions here. Here's my referencing function right here. This is pretty much my existing referencing code. I've just made a couple minor changes. The first one is here. Notice I'm not using that constant called referenced anymore. I'm using the variable that comes from the background task that's updating it. This is exactly the same bit. It's just checking to see if referenced is 1 or 0. If referenced is 1, then sit and spin. As soon as reference goes to 0, that means referencing is commenced. It'll go to the second while loop, and as long as it isn't finished referencing, and it's not inhibited, and it is enabled, then blink the light, because that means we're in the referencing process. Now, if it either finishes referencing, you inhibit the drive, or you remove the enable signal, it'll exit the while loop. And the first thing it will do is it'll just turn off the blinking light. And then it's going to check to figure out, did referencing end normally, or did you stop it early by flipping the controller inhibitor, the enable switch, to the wrong position? So it does a little if statement here and says, if I inhibited the drive or I removed enable, not enabled in other words, then I asked for a quick early stop. It'll do an R stop and it will reset the referencing bit. But if the referencing ended normally, it's just going to silently finish because it finished correctly. And it will exit the referencing function and go back up here to my endless while loop again. Okay? Good. Now, final function. This is my positioning function. Call it do position. And this is basically just my old code. I don't think I actually changed anything at all here. So this is completely the original code. It does the positioning operation. And that is it. That's all my code. Pretty straightforward. All right, well, let's go ahead and fire it up and exercise it and see how it works. Let's compile it. And run it. And before we start playing with the motor, let's just check to see if that background task is running and updating those variables. Let me point something out here. You may have noticed this yourself. Normally, only the first task changes to start when you click the lightning bolt, but notice the third one is now showing start as well. That is because that start task has happened. So set task is executed. I've passed it the start function, and that has fired up my third task. Now, task number 2 is not running because that has to be manually started, and we didn't start that. So do notice that. Remember, these 3 status indicators tell you which tasks are running. Okay, let's go to our all variables window for a second and just see if those background variables are updating. We have to find them first. There they are. All right, there's the inhibited signal, the enabled, the ready, referenced, in position, stopped, fault. All right, let's just kind of check that these are functioning. Inhibited right now is showing 0, so that means it's not inhibited. And I'm looking at my box and the controller inhibit switch is on actually, so that's true. My enabled bit is on, and I look at my box and it's on as well. Ready is true. That's showing fine. It's showing as referenced because I think I referenced the drive last time I ran it. So because I have an absolute encoder, it's still referenced. It's also in position because the last positioning operation completed. It is stopped. It's showing 0 because there's no fault on the drive. The option inputs are all 0 because all the switches are off. Option output is showing an 8, and that's because DO13 is on. That happens to have its bit in the 4th position, so that turns from binary 1000 to decimal 8. I should actually probably change these here to binary formats since we kind of care about these in binary, not in decimal. There we can see those bits showing. Of course, we can see our math variables too. They've computed just fine. Everything looks good. Looks like our background task is doing its job. Let's go ahead and exercise our program just very quickly to make sure everything works. All right, let's go ahead and start it up. I'm going to turn DI10 on, let it fire up referencing, and I'm going to turn it off immediately after that because if I don't, it's just going to jump back into referencing when we finish. So we're just going to be pulsing the control signals when we only want to do something once. So I'm going to turn DI10 on. Do notice that the bit and option inputs has turned on there, so it is reflecting a change. Now I'm going to turn it off again. My drive is referencing. I'm going to now come on the cam, come off the cam, and it stops once it goes past the 0 pulse. So referencing does clearly work. Let me confirm that I can stop it with controller inhibit. So I'm going to trigger referencing again. I'm going to turn DI10 on and then off. And then I'm going to remove controller inhibit. Click, it stops. That's good. So I'll turn controller inhibit back on. And then I'm going to start referencing again, and this time I'm going to remove enabled. So I'm going to start referencing by turning DI10 on and off. And then I'm going to remove enabled. Watch the enabled bit in the variable watch window. All right, see I've removed it there, and the drive did stop. I'll turn it back on. Everything's good. All right, so I think clearly referencing is working fine. Now I'll go ahead and fire off the positioning function. So I'm going to turn DI11 on briefly to trigger it and then turn it back off. Here we go, DI11 on and then off. And now I'm going to trigger it by turning DI12 on and off, give it that pulse to start. And there we go, it is positioning. And finally, it's going to go back to the beginning. And because I've turned off DI11, it's now just waiting again. If I'd left DI11 on, I could have triggered another positioning cycle by just pulsing DI12 on and off, but I didn't. I think we can see everything's working. So clearly we have fulfilled all our goals. All right, moving on to a new topic. I have mentioned that you can actually change some parameters in the parameter tree under program control. In other words, you don't have to go to the parameter tree and set up parameters manually. You can actually just do it through your program. I'm going to now show you a function that lets you adjust certain parameters. Not every one of them, but some of them. And this function is called setSys, and it is used to change one or more parameters. Now, as you can guess, that first parameter in the list is the parameter in the parameter tree you're changing. So which ones can you change? POSRamp can change the two positioning ramps, parameters 911 and 912. POSSpeed changes the positioning speeds, 913 and 914. Ramp type changes the ramp shape. We really haven't gotten into that in this class, but that's parameter 916. Brake changes the brakes behavior in parameter 730. We really haven't gotten into that either, but I'm mentioning it here just so you know it. There are some other parameters that can be changed, but we're not talking about them in this class, but the information is there in the manual if you wish to look it up. Okay, so the constant picks which parameter or parameters you're changing. Var is a variable that contains the value you wish to go into the parameter. So you pass it the variable and the function then extracts the value and puts it into the parameter. Now you may be thinking, all right, but what if I do POSRamp, for example? That's two parameters. Do I pass it two variables? The answer is no, you don't. You do something a little different, which I'm just about to explain by giving you an important reminder. If you affect multiple parameters when you call setSys, in other words, you're changing two at once, what you need to do is have two variables containing the values you're passing contiguous with each other in memory. In other words, one comes right after the other. So it might actually be smart to use H numbers here just so you can guarantee that your variables are contiguous. So for example, if you're going to affect POSSpeed and you want to pass it, say, H450, what you should do is make sure that H450 and 451 contain the two numbers that are going into those parameters. They must be contiguous. If you don't do that, it's not going to work right. So the variable you're passing to setSys is the first one. It will automatically go through and draw from the ones after it. Another little note, if you adjust speeds, they are in pseudo-decimal format. So if you want to put in, for example, 750.5 RPM, you put in 7505. So do be aware of that. There is one decimal point. Speeds can go down to 0.1 RPM. Ramp values are in milliseconds. So if you want a ramp of 1 second, pass it 1000. All right, hands-on task ahead. We're going to create a new program, program number 13. So make a copy of program number 12 because you're going to use it as the basis for 13. Here's what you need to do. The logic has not changed, but we're going to modify the positioning speeds and the ramps. So when you are working your way through the stations as the can is being filled, weighed, and palletized, I want you to use a positioning speed of 750 RPM with a ramp of 1.5 seconds. So you're kind of using a slower speed and ramp when you're carrying a load. But then when you return back to the beginning, you want to do that really fast because the carriage is empty. So use 1500 RPM with a ramp of 0.5 seconds. And of course, when I say use a ramp of 0.5 or 1.5, I mean that for both the acceleration and deceleration ramps. Okay, and I would like you to store those speeds in your program in constants so it's easy to change them. All right, so just a fairly minor tweak here. So pause the video and go do it. All right, well, hopefully that went really easily for you. Let's take a look at my code, and you can compare it to yours. All right, well, for this program, we don't have a whole lot to do. We're basically taking the previous program, making a copy of it, and then modifying it so that its positioning speeds and ramps differ from the loaded and unloaded condition. So in other words, when the carrier is carrying a can, it's going to move more slowly and have a more gentle ramp. When it returns to the home position, it's going to basically do it as fast as possible. Therefore, we need to use the function we just learned about to alter the positioning speeds and ramps as required. According to the instructions, we were to use constants to store our speeds and ramps, so I've done that here. I've added 4 constants to the end of our constant list. I have the constant for the empty speed, that is 1500 RPM. Remember, there is one extra decimal place because it goes down to tenths of an RPM. The empty ramp, which is 500 milliseconds, and then the loaded or full speed, which is 750 RPM, and the full ramp, which is 1.5 seconds. Our constants are in place. Now we need to do one other thing here. We need to create 2 more variables because we're going to be changing 2 ramps or speeds at a time, which means we need to pass 2 variables into the setSys function, and they must be contiguous. In other words, using 2 h variables that are right next to each other. What I've done here is I've declared 2 variables, just called var1 and var2, and I've declared them as long, and by putting them just side by side like this with no other variables between them, they should be in contiguous locations. That's all we have to do. Now we need to alter our positioning to use the different speeds and ramps. So here's what I do. First thing I do is I load the constant full speed into both var1 and var2 because we're using the same speed in both directions, clockwise and counterclockwise, so we load it twice. Then I call setSys and I tell it I want to alter the positioning speed, so I give it the constant IPOSspeed, and I pass it var1, the first variable. It will automatically find the second one. That will set the speed for the positioning speed parameters, clockwise and counterclockwise. Then I do this again, this time using the ramp values. And since I'm using symmetrical ramps for both acceleration and deceleration, I set both var1 and var2 to full ramp. Then again I call setSys, this time with IPOSramp as the first constant. pass it var1. And then all the positioning operations after this are going to use these speeds and ramps until I change it. I do that right here, right before I go to the home position, and I use empty speed and empty ramp and call setSys twice. That is all I have to do. This is pretty simple. So let's compile our code, make sure everything compiles okay, and it does. So we'll run our code and go ahead and go into positioning mode. Since I have an absolute encoder, I don't have to reference it again. It's still referenced. If you have an incremental encoder, of course, you would have to do that first. So I'll take my control box and I will go into positioning mode by turning DI11 on and off briefly. And then I will pulse DI12 to start positioning. Now watch this on the camera, and you're going to notice that the speeds very definitely are different. So here we go, triggering DI12. You can see it's positioning at a much gentler speed than it did before. It's also not accelerating and decelerating as aggressively. There's my second position. Third one. Now you should notice when it returns home, it should be a lot faster. And it very definitely is. I think that works. Okay, well now we're moving on to a new topic, and that is the subject of controlling the drive in what amounts to a speed control mode. Everything we've done so far has been positioning oriented, but usually most positioning applications do include the ability to jog the drive, to start it up either in the clockwise or counterclockwise direction at a particular speed, usually just to get it into position in some way, often for tweaking its position or working with the drive in some other way. So we generically call this jogging, but actually it's really just a kind of speed control mode. We're going to explore several different ways that we can jog the drive. We're going to do these by having you create a variety of programs, but do be aware these techniques can be used as just simple speed control as well. Now, almost all jogging techniques basically come down to modified positioning operations. What do I mean by that? Well, think of it this way. They work by continually sending the drive to a position just out of reach, and I've used two very familiar examples to help you associate this. One is a dog chasing its tail. As you know, the dog can never reach its tail. The tail's always just out of reach, and so the dog just goes round and round and round. The other is the donkey following the carrot on the stick. The carrot's just out of reach, so the donkey just keeps walking toward the carrot, never gets there actually, but it's producing motion. Jogging techniques are almost always positioning operations where you just keep the destination moving just out of reach. And if you do it right, then the positioning operation turns into just continuous motion. All right, that said, we're going to write some programs to explore this. We're going to begin with a brand new program, Program 14, and what I'd like you to do is make a copy of Program 13 because you're going to use some of the code from that, but you're going to create some new code. Here are the requirements for the program. I'd like you to modify the previous program, the one you've copied, so it can jog the drive when DI11 is on and DI10 is off. Now, if you remember, your existing program goes into referencing mode when DI10 is on and DI11 is off, and it goes into positioning mode when DI11 is on and DI10 is off. What you're really doing is replacing the positioning code with some jogging code, and the jogging code will occur when DI11 is on. So we're kind of ditching positioning for this particular program. All right, so you need to modify the function, of course, from a positioning function to a jogging function. We're not using DI12 in pulse mode to trigger positioning like we did before. We're using it for direction control. So if DI12 is on, jog clockwise. If DI12 is off, jog counterclockwise. And the minute you turn on DI11, it should just start jogging. So no pulsing to start it or stop it. DI11 is like an on-off switch for jogging. DI12 sets the direction. If you turn off DI11 or turn on DI10, in other words, exit jogging mode, halt jogging immediately. And I want you for this one to figure out a way to do this using the go relative function. So you're going to use the relative positioning function. And I'll just mention as well, I'd like you to jog at 600 RPM and use a half-second ramp. So you'll probably have to reprogram the parameters that control positioning, speed, and ramp. And I'm going to give you one little handy tip. If you call axis stop with ASP stop, that will halt a positioning operation immediately. Useful to know. All right, go give it a try. Go out and do it. All right, well, let's see how you approached it. I'm going to show you my code, and you can see if you used a similar tactic or not. All right, well, this is our first attempt at jogging. Remember, we're supposed to use relative positioning for this, and it's basically an adaptation of the previous positioning program, but we're replacing the positioning function with the jogging function. Let's go through it and take a look. First thing you can see is I've thinned my constants down considerably. I've taken out any constant that has nothing to do with this program, and I've added two new constants right here. These have the jogging speed, which is 600 RPM. Remember, that's in tenths of an RPM, so we have 6,000 there. And then we have the jogging ramp, which is 500 milliseconds or half a second. I've also cleared out the variables we don't need. I do still have these variables here, var1 and var2, because we use those with setsys to pass information into it. Of course, I've kept my background task variables here. That's going to stay in because that background process is just generally useful. All right, my main code has not changed at all, except in one respect. Instead of calling doPosition, I now call a new function doJog when DI11 is turned on and DI10 is turned off. I'm going to leave the referencing function. Let's look at our new jogging function right here. This replaces doPosition. First thing it does is it simply programs the appropriate system parameters to give us the right jogging speed and jogging ramp. So we put jog speed into var1 and var2 because we're going to jog the same speed in both directions. We call setsys with the ss_pos speed constant. Then we do the same thing again, but with pos ramp. And of course, we use the jogging ramp constant in the variable 1 and 2. All right, pretty straightforward. Now we come to our jogging code. All right, then we have this while loop here, and that determines whether we're in jog mode or not. It masks the option inputs variable, so we're looking at just the bottom 2 bits. And as long as we get a 2 out of that, which is what the jog mode constant is, then we continue in the while loop jogging. If we turn the switch off that activates jog mode, which is DI11, we'll exit the while loop. Also, if we happen to turn on DI10, we will exit the while loop because that's going to change the number from 2 to 3. We're ignoring all the other switches, which is important we do that because we are using DI12 to control direction, so we don't want that interfering with anything. So as long as we're legitimately in jog mode, the while loop keeps looping, and it does one basic thing here. It looks at DI12 to determine the direction of rotation. So if DI12 is on, we're going to rotate clockwise. If it's off, we rotate counterclockwise. We do exactly the same thing for rotation. We call go rel, and we call it no wait. It's very important to call it no wait. If we call it in wait mode, we're not going to be able to exit nearly as quickly because it's going to just sit and hang until it completes the positioning operation. So turning jog mode off may take a long time to exit. Notice I request a relative rotation of 4,096 increments. That is 1 revolution. So basically, I chase my tail by just setting the destination 1 rotation away from me, and it causes me to turn in that direction. If we're going in the counterclockwise direction, we just chase in the other direction, minus 4,096. As soon as we exit the while loop, which would happen by exiting jog mode, we do an access stop here, and we use p-stop. That's the positioning stop, which is the kind of the normal stop for positioning. Okay, pretty simple, relatively straightforward. Let's see how it actually behaves. I'm going to compile my code and run it. I'm just going to pick up my control box. I'm going to turn on DI11 and see if the drive starts turning. Here we go. DI11 goes on. And yes, indeed, we are starting to rotate. We're rotating counterclockwise because DI12 happens to be off. Let me turn off DI11 and see if jogging stops immediately. And it does. It stops promptly. Turn it back on. Continues rotating. Now let's try the other direction. I'm going to turn it off. Drive stops. I'm going to turn DI12 on, which should pick clockwise rotation. I'm going to turn DI11 on. And indeed, it is now rotating in the other direction. So that works pretty well. Now let's look at something here. I'm going to turn DI11 back on again, and I'm going to change direction. Watch the drive. Notice it doesn't change direction right away. That is because it's trying to complete the positioning operation that you've sent it, and they actually start building up. So what's going to happen is it may take a number of turns before it finally catches up and it changes direction. That is kind of a downside. Now, we could certainly make it a little more responsive by shortening the distance we're traveling. Maybe we don't go a full rotation, maybe we just go a partial one. But in that case, we might actually get a slightly rougher jog. So this method is not perfect, and that's why we're going to explore some others as we go along in this session. And guess what? You're going to get to write another program. We're going to use your existing program that you just wrote, program 14, and make a change to it. And here's what I'd like you to try. We're going to explore an alternative jogging technique. And I'd like you to modify it to use Go ABS instead of Go Relative. And I'm going to give you a suggestion that might help you. IPOS motor, which we've talked about a few times before, located in H511, it's one of the system variables, contains the actual position based on an X15 connected encoder, in other words, the motor encoder. You can use the information in there along with Go ABS to come up with a jogging strategy. So, go out and figure out how to do that. Okay, well, let me show you my code and you can compare it to the strategy you used and see if it is similar. All right, well, this is the second version of our jogging program. The only difference was we were supposed to use absolute positioning instead of relative, so there are only a few lines of code that are different. In fact, this is it. Notice we've replaced Go Rel with Go ABS. We're still using no weight. Now we have to approach this a little differently because, of course, with absolute positioning, you can't just give it a relative offset. You've got to give it an actual real position. So what I've done is I've used the system variable IPOSmot, which is the current position the motor encoder is returning, and I just take that number, in other words, where I am now, and I add or subtract 4096, which is one rotation to or from it. And that's all I do. So that's really just, again, tail chasing. I put my destination just a little bit out in front or behind me from where I currently am, and I say, go there. And that is all I've done to change this program. This is a very trivial change. Let's compile it, run it, and see how it differs. All right, I have my control box. I'm going to go into jog mode by turning DI11 on now. You can see it's spinning just fine. Turn it off. Stops just fine, nice and quickly. Let's check the other direction. I'll turn DI12 from off to on, and then I'll turn DI11 back on. Jogs the other direction just fine too. Now let's see how it changes direction while it's running. Remember, with relative positioning, there was a lag because there was sort of a built-up bunch of Go Rel commands that had to execute first. Let's see if Go ABS is better. I'm going to turn DI12 off right now. And I'm going to turn it on right now. And you can see it's changing direction very promptly. So this is clearly a better strategy than using GoRel. GoABS does seem to be a good solution to very responsive jogging. And guess what? We're going to do another program. You're probably really starting to hate me, all these programs. We're going to modify our existing program again to explore a third jogging technique. And let me give you some suggestions as to how you might achieve this. I'd like you to modify your program so it doesn't use either of the positioning commands. Now you're probably thinking, well, then I have no idea where to go from here. Well, I'm going to give you a few tips. First of all, I'm going to point out another system variable, target pos, which is in H492. It contains the destination position of the current operation. In other words, if you call GoRel or GoABS, you will see this variable change. It will have the destination position. But of course, you can change this variable directly. And if you happen to change this variable when the drive is enabled, guess what? It will take off and try to go to that position. And here's another thing to be aware of. You can change that variable when the drive is running. All right, maybe that will spark a few ideas, so go out and give it a try. Okay, well, let me show you how I approached it using target pos, and you can compare that to your code. And we now come to our final jogging program. This is the one we're not allowed to use either GoRel or GoABS. We're going to have to use a different technique, and I gave you a hint to help you do it, so hopefully you figured it out. Let me show you the change I made from our previous program. Again, it is very, very trivial. Just 2 lines of code are different. Remember, I told you about a system variable called target pos that holds the value of where the drive is trying to go when it's enabled. And I mentioned 2 useful facts about it. One, if the drive is enabled and you change it, it will cause an immediate change of motion. And also you can change it while the drive is running. So I did basically the same thing I did with GoABS. I took the current motor position, which I read from the system variable actPosMot, which shows just the current position coming back from the motor encoder. And I added 1 rotation to it, or I subtracted 1 rotation from it, telling it to go to that location. And I changed target pos with that value, and that should cause it either to move forward or backwards by 1 rotation from wherever it is. Let's see if this works. Compile our program, run it, pick up our control box, and give it a whirl. Okay, here we go. I'm going to turn DI11 on, and off it goes. Runs just fine. Turn DI11 off. Stops just fine. Turn DI11 back on, and let's try going back and forth. We'll scrub it back and forth by switching DI12 on and off. And it most certainly is working just fine. So I think this method is really in some ways our nicest jog strategy, but all 3 of them do have their merits. All right, well, we are now finished with jogging. I'm sure you are utterly sick of jogging. We're going to look at a few final topics, and then we're going to wrap up. I'm going to show you another function in the library of IPOS function calls. This is called the system access function. It allows you to access certain pieces of information available within the VFD. The function is called getSys, and it reads a system value and deposits it in var. So you pass it a variable which will be the recipient of the value it's going to read, and then the second parameter, sysval, indicates what you want to look at. There are a number of possibilities, but these are the 3 we're going to talk about right now. There are 3 constants available: GS act speed, GS error, and GS AN inputs. Act speed reads the current motor speed in 0.1 RPM units. So in other words, there's like a pseudo decimal place If you're turning at 100 RPM, you'll actually see 1000 come back in the variable because there's that imaginary decimal, so you can check the motor's current speed. GS error reads the VFD's current error code, so if the VFD faults, you can read the error code to know what happened. And AN inputs is probably the most interesting because it reads the two analog inputs on the VFD. This allows you to access some non-digital information, some analog information. And just a heads up, the values are normally plus or minus 10,000 millivolts, in other words, plus or minus 10 volts, unless there is a current-based mode active in the VFD, but normally it's a voltage, so plus or minus 10 volts expressed in millivolts is the maximum range. And again, if you are trying to read something that returns multiple values, then you'll need to have enough contiguous variables to hold the results. var is the first variable, and it will deposit information into subsequent ones until it's read everything it's supposed to. And just be aware this is not a complete list. You can read the manual to learn what else you can access. But these are the three that I thought were the most useful. We're not actually going to write a program to explore these, but I did want to just touch on them very briefly. All right, and now finally our last topic of this session, and that is working with the non-volatile memory in the VFD. The way the non-volatile memory works is a little bit confusing. Now, I introduced you to it way back in the beginning of the course, and I kind of simplified it. I just told you the first 128 H variables were non-volatile. Well, that is true, but there's a little more to it than that. And so now I'm going to explain the entire picture. I don't think you would have really appreciated it way back then, but you're ready for it now. All right, let's take a look at data memory again. Data memory is divided into two sections. There is H0 through H127, and there's H128 through H1023. Now, it may surprise you to learn that actually all of this memory is volatile. In other words, it will lose its contents when you turn power off. And you're probably thinking, wait a minute, you've been telling me over and over that H0 through H127 is non-volatile. Well, the answer is, it is and it isn't. Let me show you what's going on here. Normal data memory, H0 through H1023, is volatile. So when you write information into those variables right at the beginning, it's normal volatile memory. But here's what makes them non-volatile. There's actually a second memory that shadows this area, and it is a flash memory, which, as you probably know, is non-volatile. What this means is the contents of H0 through H127 can be transferred into flash memory where it will then be protected against a power outage. So it's kind of like this. During normal program operation, H0 through H127 and H128 through H1023 are identical. If you turn off the power, everything will just evaporate from any of those locations. However, to preserve something in H0 through H127, you can execute a function call, which will store those variables in flash memory. So you can protect them, but you have to do it intentionally. If you don't do it and you turn off the power, they're gone. So it's kind of like this. You can transfer them. Now, this is automatic. When you turn on the VFD, what it always does automatically is it reads flash memory into H0 through H127. So it will read back the flash memory on power up. And if you took the trouble to transfer things across before you powered down, that information will be preserved. So transfers in this direction. There is also a function call that will force a retrieval from H0 through H127, but normally you don't have to do that. Normally it's retrieved just on power up. Okay, before we look at the magical function that does this, let me give you a few application notes. First of all, non-volatile memory is a great place to store program parameters that may need to be changed in the future. In other words, instead of storing them as constants in your code, just put them in non-volatile memory, and that can then be loaded by the program into the application. That way, if you've got to change some parameters, you don't have to go in, modify the code, and recompile it. You just go into non-volatile memory. So this eliminates the need to edit and recompile the program. So kind of things people often put in non-volatile memory would be things like gear ratios, roller diameters, speed set points, ramps, positions, things like that. Now, how do you do it? Remember, you can modify flash memory with the All Variables window. If you edit those locations, H0 through H127, it will automatically flash the memory. So that means a user, instead of having to mess with the code, just has to go into the All Variables window and change a few memory locations. This is a more elegant way to get around having to change constants in the program. This may be something down the road for the senior project program you may want to play with. All right, now let's look at the function that accesses flash memory. It is called memorize, which is kind of a nifty function name. And it has a single parameter which indicates what you want it to do. Mem_st data and mem_ld data, you can probably guess what these do. St data stores all 128 variables from H0 to H127 in flash memory. And LD data retrieves them from flash memory back into just the regular volatile memory. So normally you don't use the second one much, but the first one definitely. Let me give you a little tip here. After you call this function, do a wait 100 to create a 100 millisecond delay. This is necessary to allow the function to complete correctly. If you don't do it, you can get into some problems. So just do a wait 100. And this list is not complete. There are some other parameters and other things available. I'll leave that as an exercise for you to look up in the manual. And guess what? We are not writing a program, so we are at the end of our session. I hope all that jogging didn't drive you crazy. We are at the end of session 11, and this wraps up our advanced session. So now we're going to move in session 12 into our senior project. So see you then.